Today's show, we will look at the volcanic rocks from around the world. You'll see it's exciting. I have here Google Earth so I can show you different rocks from around the world. The first rock we're going to see today is a rock from the United States. And let's see if I can show you right here. So this rock here is from Mount St-Hélène. Mount St-Hélène is a volcano in the United States. The last big eruption was in 1980. And in about, I think it was in 1998, I went for a car ride to Mount St-Hélène to have a look. I wanted to collect some samples. And if some of you says, well, I don't know if I've touched volcanic rocks from an explosive volcano, keep in mind that another word for this is pumice. The word we use in geology is rhyolite. So let's see if I can look at the volcano with you. So first of all, let's see if we can go here. We're on Earth here. Let's see if we can get closer. I'm going to go here. We're going to look at Mount St-Hélène. Mount St-Hélène, like this. Let's see if it's going to find it. There we go. Perfect. So here we are in Washington State. And we have here 3 volcanoes here that have erupted in the last 100 years or so. We have Mount Rainier, Mount St-Hélène, and we have another one right here, which is Mount Adams. So Mount St-Hélène is this one right here. So here in 1980, what happened here is that there was an earthquake, a side of the mountain slid away, and it erupted. You could see how we have here all the lava and the debris that flew out of the volcanoes. And here you can see some snow on the surface right here. What was interesting, so here, if I go back to my sample right here, so if you can see, this is a very light rock. So here, this is like if you have whipped cream in a compressed container. When you shake the container and you put whipped cream on your coffee or your dessert, you have a small volume and it increases and you end up with whipped cream on your plate. It's more or less what happens in a very highly explosive volcano. So you have here magma that is compressed in the Earth's crust, and then there was an earthquake, there was a zone of low pressure, and the lava was able to go out. And because there's a lot of gas here, as soon as the pressure releases, it expands very quickly and it becomes very explosive. So it is very light in color, and the reason for that is that it is a magma that evolved over the millions of years. So a lot of the atoms and minerals that were rich in iron and magnesium have settled. So here we have a composition much more rich in silica, for example, silicium, we have sodium, calcium, aluminum, and so on. So here is the first volcanic rock I have for you. Very nice. I remember when I was on the mount, it was about, let's say, 18 years after the explosion. So when you were on the road, it was very white in color. And if you just went off the tracks of the vehicles, it was so you could step on the sediments and it was very friable, and you just compress and you would sink. It was quite nice. I brought a few samples back from that trip. So as you can see, we have here a rock that is very light in color. The next one we're going to look into today is the volcano from Costa Rica. So let's see. Volcano. So let's see what we have. Oh, it's going to figure out. Oh, I think I went too fast. Let's see. You can find it. There we go. Let's see. It's right here in Costa Rica. Now, what's interesting here is that we have here lava in the crust that is evolved in Washington State, and we have very explosive volcanoes. All along the Andes here, we have volcanoes. Now, the lava is a bit more evolved. We call it andesite. And what happens here is that there's a lot more iron and magnesium. They're not as explosive, and there's a lot, so it creates often cones with respect to what the volcano looks like. I'd like to think of some of the volcanoes in Italy, for example, the Mount Etna. Yes, there's also the Mount Fuji in Japan, which are like a very big cone. These are examples. It is quite rich in aluminum, silicium, sodium, and carbon. And let's see, calcium and sodium, there you go. But there's also still a lot of iron and magnesium. So there's it's a bit more solid. And that's why we have those cones. So here we have, let's see if I can make it a little bit bigger for you. So as you can see, it forms a cone like this. Let's see if we can make it closer. I went there earlier to have a quick look. Perfect. So there are several volcanoes in Costa Rica. As you can see here, we have an old crater right here with the lava in this part, and here there's a much newer one. So I was there in 2004, and you could see, so I picked up a sample. Now the sample here was not right by this volcano. It was close to another one in Costa Rica, but let me show you what it looks like here. So this one here is, so this one is andesite, so it's darker in color to start with, and it's also a reddish color. So here the content of iron reacted with the atmosphere. So for this one here, it's quite solid. I'm not sure when the eruption was. I figured a couple decades ago, and it's solid. And you could see that there's an alteration here, much darker compared to pumice from Mount Ste-Hélène. So you can see the difference here. So when it came out, it was probably in a grayish color, and compared to a light color like this one right here. So this is our second volcano today. The third volcano I want to have a look today will be from Hawaii. Let's see. Oops, let's go. You can do this. I'm going to go away a little bit. And where's Hawaii? It's just right here. Now, what's interesting with Hawaii? So I'm going to have a close-up, and then we'll go a bit further. You'll see it's exciting. So Hawaii is a volcanic island. So what we have here, there are two big volcanoes. There's a Mauna Loa and the other one. Mauna Loa, and what's the other one? I forget the name. I was researching later. So Kīlauea and Mauna Loa. There we go. So here we have two volcanoes. So I have a friend who went to Hawaii. I've never been there yet. It's part of my list of things to do. And here you could see. So it is a magma that is much darker in color. So we call them basalt. So if you can see the difference in color compared to Mount St-Hélène. So this one is much primal lava. So this lava here, as you can see, it's from the mantle, much more rich in iron and magnesium. It's darker in color. And I have a few samples from Hawaii. So here you could see there's some gas here in there, and it was able to solidify with the gas bubble. Let's see if I can get it closer. It's always nice. So here we have here a layer of lava. So you could see here, you could see some of the small holes where we had some gas. You can see some minerals forming slowly. And you could see here we have on the surface, it's solidified. So it's like when lava flew down. So here it's not explosive at all. It's like it oozes out. The reason it's very, very viscous. And what happened here, when it comes out, the surface cools down, and therefore you have a flat surface that is insulating lower lava flow. So here you could see under, I have some grooves, and the grooves are probably where the lava was able to flow from under. So it's kind of exciting to see. And we have here another one. It's a bit smaller, this one here. So you have a crust right here. And we have here some ridges. If I remember well, the texture is Behoihoi, if I remember well for the name. So here what happened is as the lava came down, the surface cooled down, and it just kind of folded, made little folds as the lava was coming down. So as you can see, and that's under where we have some of gas bubbles, but it's a much darker color. So if you look at the difference, these are volcanic rocks from Hawaii. This is the one that is from Costa Rica, much lighter in color, and the one from Mount St-Hélène. Big differences in colors because there's a big difference in composition as well. Perfect. And we're going to go to the fourth volcanic rock that I have. So volcanic rocks from the fourth place. And let's see if you can see what it is. So we're going to back up a little bit. Oops, that's not the place. I want to go right here in Iceland. So what we have in Iceland, we have here a volcanic island. And here this island is along fault or edges of different plate tectonics. So if I step back a little bit, you can see the ridge here. And then if you go down further south, you have the ridge right here. Let's see if I can make it bigger for you. There you go. So here you can see the mid-ocean ridge here in the Atlantic. And we have Iceland right here. So what happens here in the Atlantic? So you could see that Europe is going further away from, let's pick two. So we have Ireland here that is going away from Nova Scotia or the Quebec province, maybe a few centimeters a year. But you know what? That ridge is along the whole Atlantic Ocean. So here we have Western Sahara going away from Florida here in the States. And if you go further south, you have here Sierra Leone getting away from French Guyana. And if you go a bit further down, so here we have Namibia that is going away from here, let's say, I want to see Uruguay, but that's Uruguay right here. But if you go right in the middle, you could see here, there's a ridge right there. So it is going apart like this. They are going away. So new lava is coming through. So here, the ocean floor will be the most primal lava we can have. The lava from the earth, from the mantle, very rich in iron, magnesium. Last week, I did a video a couple of weeks ago on ultramafic rocks from the Eastern Township in Quebec, where we had very, very dark rocks made in the ocean floor. This one here, high content of hydroxide, some chlorine as well, due to the alteration and the ocean water at the time. So let's go back to Iceland right here. So if we go up here, so you could see there's a ridge all along here. So we have here, in English, we call those hotspots. It's a place where in the mantle, it's like there's a highway of lava that can come up and it's continuously outpouring lava. They're not explosive. They go up and then they flow and they make new landscape. So here we have Iceland. I had a friend who, not a friend, but a student of mine went to Iceland a couple years ago. And as I said, if you have a chance, bring me a rock. And that's the rock that he brought me. So as you can see, the rock is also very dark in color. So this is probably a decade or two in age. As you can see from Hawaii, very dark colors. It looks a little bit lighter, but I would need some composition to be able to make the difference. But it's interesting. So here you can see the lava as it was cooling down, it was rotating, and it's like a twist. There's a twist in that rock right here. So this rock, right from the mantle, very rich in iron and in magnesium. That's why it makes it this dark like this. So these are three rocks that I wanted to share. So plate tectonics is interesting because it tells us how volcanic rocks can be. So here we have Iceland, where we have magma coming from the mantle. If you go right here in Hawaii, oops, let's see if I can put the map back. In Hawaii right here, we have volcanic rocks, and here we have also a plume. So we have magma coming from the mantle, and that spot hasn't moved. However, if you look at this volcanic island here and the smaller one here, you have a series of underwater, like a volcanic mount under the sea level. And if you look, it goes along a trace right here. And actually, you can see the trace going this way and then going up like this. And the reason for that is that we have here a hotspot, lava coming out, making new islands. But over the millions of years, the specific tectonic plate is moving over that hot spot. So here you could see that the plate here is actually moving towards the west like this. So that means that maybe not in our lifetime, but what will happen is that eventually it will move and there'll be a new volcano that will be created here next few hundred years, few thousand years, a few million years, to continue with that trend right here. Then again, we have magma coming from the mantle, very, very dark in color. If you think of the volcano from Costa Rica, what we have here, we have subduction zones. So that means that we have here very dark volcanic rock that is going under this continental, let's say, like in Canada, we call it the Canadian Shield, but it's the surface where the rock is much lighter. So as it goes down, this rock is melting. But here on the edge here, we also have rocks that are melting, and there's a mix of water, sediments, and therefore we have volcanic rocks that are much more, that are not as rich in iron and magnesium, but there's a mix of different composition. And if you think of the Mount St-Hélène right here, the reason why this one is quite light in color is that we have a volcano. Let's see, it's the volcano right here. This volcano here, we have magma that was able to sit in the crust here, had a chance to evolve with the millions of years. So it didn't take its time to come out, but it had a chance to evolve, and therefore just leaving silica, aluminum, calcium, sodium, much lighter elements that created this magma right here. And these are the different volcanic rocks I had for you today, but I'm going to add a few more rocks for you because it's always interesting to see what happens if we have magma. Instead of coming out of volcanoes, what if they stay underground? So here I'm going to give example with the rhyolite here. So rhyolite, this rock here is very light in color and was able to come out of the Earth's crust through a volcano. What happens is that sometimes we have magma that never makes its way out of the Earth's crust, but has a chance to cool down slowly. So here's an example of rhyolite. So this one is extrusive. This one is intrusive here. So we have a rock that is light in color. It's here, this one is pinkish a little bit. You can see the little white dots. So we have some minerals that are starting to grow, but it's not well defined. So that means that this, we had magma going into the crust and cooled fairly quickly, but slow enough to be able to have some minerals growing. And you're going to say, where did I take this? This is what we call from a rhyolite dome. And the rhyolite dome is from one of the France territories. So it's not from France here, but if you go here in by, oops, I need to show you the map. I think that's much better. So we have a France that is right here. Let's see if I can make it closer. So France is right here, but if you go back 400 years, they had colonies in North America, and it was given to to England, all kind of geopolitical situation. But if we have here Newfoundland, you have here two islands, St-Pierre and Miquelon. And if you go here, we have here two islands. One looks like an hourglass, the other one is an island. And if you look, the reason why France decided to keep these two islands was to be able to keep fishing rights in this area to send back the fish to the mainland, which was France. But if you go here in St-Pierre, I'm going to get closer like this. So a few years back, I went for a drive, went to St-Pierre. We have the town right here. I went for a hike up the mountain, and here, this whole thing here is a rhyolite dome. So it was magma that was able to cool fairly fast, but it was a dome. Because it's rich in silica, it's very, very hard. So that made basically the shape of the island. So we have here an example of what we call a rhyolite that was able to cool down. And you could see the little white specks. Some of the minerals were growing. Now, if we have rhyolite that doesn't go out of the crust as a volcano, but has more time than this rhyolite to cool down, we end up with what we call granite. So granite, if you think about it, it tends to be pinkish in color, like this one here, and it has the chance to cool down slow enough so that the different particles and molecules were able to arrange themselves. And then you end up with a piece of granite. Let's see if I can wet it a little bit. I don't know if I will be able to see it. Let's see, there we go. So we're able to see the different grains within the granite. And here it's a light colored rock. The reason why it's light is it's rich in silicium, aluminum, calcium, sodium, and so on. And that's what made those minerals. A rock that is quite light in colors. But the composition of this granite and this rhyolite here from a rhyolite dome and the composition of this rock from the Mount St-Hélène, they're somewhat similar, and it's interesting to see how it goes. It all depends on how much time they have, how much time the lava, the magma coming up, has a chance to cool down. If there's no time and it comes out of the crust, it becomes lava. If it stays at close to the surface but cools very fast because maybe it's close to water or I don't know what, it becomes a rhyolite with very small grains. And if it happens that it has time to cool, millions of years to cool, the heavier elements and the heavier molecules settles. There's less and less iron and magnesium, and therefore we have a lighter color. And that is the difference between these ones. This granite here is from an area called Thunder Bay in Ontario. And I went there because we were able to go with a hammer to get some amethyst. I don't know if we can get look at this. So amethyst is the gem of Ontario, and I wanted to go with the family to see how this was. It's always nice to collect some minerals. On this is the information we have for us today. Let's get our planet. It's always nice to think of our world as a nice place to stay. If you've enjoyed the video, please put a thumbs up. If you have questions related to science or any questions about geology or space exploration, put your questions in the comment below. Otherwise, I'm going to put here a link. Let's see if we can. Let's see. There you go. I'm going to put here a link to another video that you will enjoy. See you there.